Greetings of the day to everyone and welcome to my presentation. First of all, let me thank you for your presence. I would also want to express my gratitude to my co-authors for providing me with the inspiration and direction I needed to complete this study. In addition, I would like to thank the I2CT for providing me with the opportunity and platform to share the results of my study with the international community. I am Shiv Shambhu Chaudhary, PhD research scholar in the Department of Electrical Engineering at NIT Uttarakhand. I am interested in exploring the techniques related to the improvement of power quality in the presence of renewable energy. Today, I will be sharing my research findings concerning to the operation of solar PV array under partial or complete shading, and the title of the presentation is Investigation on the Impact of Partial Shading on Solar Photovoltaic Array, and the paper ID is 1392. The outline of the presentation will be: first, we will be covering the introduction to the problem of partial shading. Then the problem statement is formulated. Following the problem statement, three test cases are modeled to analyze the performance of the system. In the scenario 1, we have connected 23 modules in series. In next scenario, we have connected two strings in parallel to form a series parallel configuration. One time the length of the string is chosen as 23 modules and it is called as longer string, and the other time the length of the string is chosen as 5 modules and it is connected as and it is called as shorter string. Further, in the next investigation, an array of 5 cross 5 module is formed and different types of shading pattern is given to the system and its effect is investigated. In the next section, we will be covering the results and discussion related to the outcomes of the experiments. In the final, we have concluded the paper and some scope for future work has been presented with the references at the end. So coming to the introduction, the solar photovoltaic business has expanded rapidly in the recent years and experts have predicted the growth to continue in the upcoming years. The pattern is mostly due to the declining prices of PV power and the widespread adoption of PV systems that are connected to the electric grid. Hence, the cost of generation from the solar PV power is now become competitive to the conventional power generation system, and hence these renewable energies are very popular nowadays. Consequently, PV module manufacturers are providing more potent PV modules tailored for building integration with advanced features for tracking maximum power from the installation. Grid connected systems are typically installed in rooftops or urban areas, and they are prone to the event of partial shadowing. The basic principle of operation of solar photovoltaic technology is the conversion of light energy into electricity energy. The basic conversion of photovoltaic technology is the conversion of light energy into electrical energy. Partial shading can have a significant impact on the output of a photovoltaic system. The nature of the functioning of a photovoltaic system, which majorly rely on solar irradiation to make electricity, leads to an implicit belief that the maximum power of a partially shaded system always drops as the system gets darker, though it has been indicated in the literature that this may not be the case. When a critical point is reached, partial shading patterns may become quite resistant to the shading heaviness, allowing a solar photovoltaic system to produce its maximum power even when partially shaded. This research looks at how the introduction of partial shading affects the locus of interest. It also deals with the safety of the system. Whenever there is a chances of partial shading, there is a possibility of occurrence of hot spots. It will develop when one of the solar modules, which is normally a part of the string of big connected series connected solar modules to form a string, becomes reverse biased and causes the electricity to be wasted as heat. If the power lost in such circumstances is greater than the maximum power that the cell can sustain, the cell will be permanently destroyed and open circuit will be developed. So as mentioned earlier, most producers include bypass diode in their PV modules as a means of mitigating the creation of hotspots under the partial shadowing conditions. Coming to the problem statement, solar PV systems are designed heavily to generate as much clean energy as it can be possible from the sun. The array output, whether we want or we don't want, are affected by many parameters such as weather, solar irradiation variation, dust buildup, obstacles due to the wind movement, PV array placement, and shading patterns. Many of the factors can be in the impact of many of the impact of many parameters mentioned above can be reduced, such as the dust buildup can be reduced by proper cleaning of the modules. The PV array placement can be checked in the design side. However, the mismatching power loss between the PV modules and the high number of maximum power shown in the electrical characteristic of PV array caused by partial or complete shadowing is a well-known and acknowledged issue that reduces the output power of a PV array. Simultaneously, it also affects the PV and VI characteristic of the modules when they are linked together to join in a fashion to form a series parallel configuration to form a large solar farm of the level of megawatt level. In order to generate electricity at the megawatt level, megawatt scale photovoltaic systems typically employ several thousands of solar modules. In order to create numerous photovoltaic modules, they are linked together in series. However, if they are purely connected in series, the output voltage of a series connected photovoltaic module will be too high to be connected to the grid connected inverters or energy storage device. Hence, to overcome this problem, the modules are linked together in series parallel configuration to derive the required amount of power which is needed from the system. The challenge in front of us is now to develop the PV characteristics similar to those of the photovoltaic modules in order to monitor and collect the maximum amount of energy from a solar string or array. Hence, the primary objective of this paper is to model, simulate, and investigate the effects of partial shading condition on the electrical properties of the series parallel PV array topologies under a variety of shading conditions, which include short and narrow, short and wide shading, long and narrow, long and wide shading, and diagonal shading patterns. The Kyocera KC200GT PV modules are used for the modeling as per the dataset requirements. The dataset claims that the system can handle a DC link voltage of 600 volts safely without any issue. Hence, 23 modules are considered as a single bigger string, and the effect of shading is explored by altering the number of modules while shading is in action. So, coming to the discussion of the test cases, the first test case is 23 series modules connected in series. The analysis starts with 23 modules in a series configuration, and the shading pattern is analyzed as the number of modules under the shading pattern is increased. It has been noted that the performance of the string decreased as the number of modules under the effect of shading has been increased. Then an attempt is made to define the secure working range for modules connected in series. In the next test case, we have used two strings in the form of series parallel configuration. The strings have different lengths. For one string, we have used 23 modules. Hence, 23 modules are connected in series to form two strings, and they are connected further in parallel. Similarly, a shorter string is used, which has five modules in one string. 23 and 5 modules are chosen as an indicator for large and short string length. Due to the short length of the strings, 20% of the impact is contributed by a single module in the smaller string. After that, to make the new test case, an array of 5x5 modules is formed by connecting them in series parallel configuration, and it is tested under different types of shading and see how they turn out. So the different types of shading patterns which are observed for the analysis are short and narrow shading, short and wide shading, long and wide shading, long and narrow shading, and table 5 representing the diagonal shading. In all these shading patterns, we have S1, S2, S3, S4, and S5 as the string length, and R1, R2, R3, R4, and R5 as the row where the modules are present. Hence, in the short shading, we can see only 3 rows are under the effect of shading, whereas in the long shading, all the 5 rows are under the effect of shading. In the narrow shading, 3 strings are properly working and 2 strings are under the effect of shading, whereas in the wide shading, only 1 string is under proper condition and rest all the 4 strings are under the effect of shading. In the diagonal shading, all the diagonal modules are under the effect of shading. So coming to the results and discussion. The first result discusses the performance analysis of a string of 23 modules of PV array for 600 volt utility grid. In the first graph, the single axis graph, and the second graph is multi-axis graph. In both the graph, PV string power and PV string voltage are plotted with respect to the string current. First of all, we have seen the behavior of the system. Seen the behavior of the string when there is no modules under the effect of shading. The power received from the string is maximum, which is close to the mathematical power, that is 4600. However, when one of the modules is put under the shading condition, then the value of power, voltage, and current all decreases. Similar thing happens for the second module and third module. However, we can see when 4 modules are under the effect of shading, then the power decreases to a value from where it is increasing as the number of modules under the effect of shading is increased till the value of 8. As more and more modules are shaded, once a limit is reached, and after that the system becomes irreversible and the string will be, and it is better to bypass the string to avoid the permanent damage or failure of the system. For this analysis, when more than 12 modules are put under the effect of shading, then the power of the system decreases to very low value and no further improvement is seen. However, from this analysis, it can be seen that there exists a safe operating area for the modules to be shaded. Next comes the performance analysis of 2 strings connected in series parallel configuration. Here what we have done, we have connected 2 strings in series parallel configuration and formed 2 systems. One system has 23 modules connected in series and it is called as longer string, and the effect of shading is observed by keeping one string at full irradiation all the time and the other string is tested under the varied irradiation level from 1000 to 0 to calculate its efficiency. Similar phenomena is observed for a sorted string where the string length is of 5 modules. We can observe from the data that the performance efficiency of the system increases though marginally, and it is not dependent majorly on the length of the string as against to the number of modules under the shading effect. So it can be seen that the when the two modules are connected in parallel, when two strings are connected in parallel, for the shorter string, the efficiency becomes 21.53%, whereas for the larger string, the efficiency becomes 22.03%. These are more than the claimed efficiency of 16% from the dataset values. When the two modules are under the effect of shading, the power is decreasing and it becomes constant at a value 8628 watts. Similarly, it is observed for three modules under the effect of shading and the power becomes constant at 8254 watts. For four modules, the value becomes 7849 watts, and for eight modules, the power settles down to 6163 watts. And the efficiency of the system decreases from 22.03% to 15.81% when eight modules are under the effect of shading. This is coming closer to the value that is claimed in the dataset by the Kyocera KC200 GT or the Kyocera KC200 GT module. When the shorter string is considered, it also settles down to a value of 1643 watts when the system is tested for various level of irradiation. When two modules are under the effect of shading, the value settles down to 1215 watts. When 3, 4, and 5 modules are shaded, the value settles down to 994 watts approximately. Hence, the conclusion that can be drawn from this analysis is that when more than 50% of modules are under the effect of shading, it is advisable to bypass the string to save the system for further uses. These are the maximum power point curves drawn in different types of shading patterns. This is the curve. The figure A represents the short and narrow shading, and the PV array current and voltage are plotted with respect to the PV array power. Similarly, in the figure B, we have plotted the PV array current and voltage with respect to PV array power. So from the short and narrow shading and short and wide shading, it can be seen that the maximum power that the system can produce is above 3500 watt in the case of short and narrow shading, and in the case of short and wide shading, it is less than 3000 watts. Similarly, in the long and wide shading, it can be seen that the maximum power that can be produced from the system is less than 3000 watts. It is coming more closer to 3000 watt in the long and narrow shading. In the diagonal shading, again, the maximum power that can be expected from the system is more than 3500 watts. And in the ideal scenario, when there is no shading impact is taking place, then we can see there is no deviation in the VI curve and it is smooth. And the maximum power that can be obtained from this system is nearly close to the 5000 watts. So the conclusion from different shading pattern is that pattern on maximum power point. The contribution of voltage and current during the maximum power point throws light on the behavior of the system under different shading patterns. Power is represented by points 1 to 7 in various shading configurations, including short and narrow, short and wide, long and narrow, diagonal, analyzed system, ideal scenario with no shading. We can observe that under ideal scenario with no shading, the maximum power that can be obtained from the system is nearly equal to the mathematical power that can be obtained from the system. And the voltage and current contribution is 129.6 and 38.32 respectively. When there is short and narrow shading and diagonal shading, means type 1 and type 5 shading, we can observe that the current contribution is nearly equal. However, there is very much deviation in the voltage contribution. But they are similar in nature because the number of modules under the effect of shading is nearly equal. In the type 2 and type 3 shading patterns, we can see the voltage level has increased from the ideal scenario with no shading impact and the current contribution decreases, which leads to the reduction in power of the system. Under long and narrow shading that is represented by type 4, we can see the voltage has reduced slightly and the current has also reduced slightly to give the required maximum power to the output. Hence, the conclusion that can be drawn from this analysis is that the effect of a string length on the efficiency. This research reveals that the efficiency of the string increases though marginally when they are linked in parallel. Extending the length of the string has considerably lower influence on the efficiency of the system, and it is greatly impacted by the proportion of modules that are subjected to the shading impact. After the analysis of critical points, it is shown that there exists a range for the safe operation of the PV array. If the string under the shading is more than 50% of the string length, then it has to be bypassed for safe operation of the system. However, this poses a challenge for the current stress load. This information can be used to design the safety and protection system of the solar photovoltaic system. This analysis also throws light on the presence of the problem of global maxima. This study adds the problem of existence of global maximum power point under different types of shading pattern. The effect of shifting of maximum power point owing to the shading effect is also explored. The future scope of the work. While just only 5 cross 5 arrays are investigated in this work, this study can be extended for a larger string count. The finding of this study have promising implication for the fields of array reconfiguration and string protection, both of which are critical for minimizing the power losses due to the hotspot formation and maximizing the usable lifespan of the solar photovoltaic arrays. These are the references that I have used for the preparation of this paper. Thank you. These are the references that I have used for the preparation of this paper. Thank you all for the patient listening, and I will be happy to answer any query regarding to this presentation.